Good afternoon, everyone. I am Şamil Çetinkaya, and in this video, I will try to answer the questions that are asked in the homework 4. So, first question is, explain the physical structure of a DC machine with the help of a drawing. Show the field and armature components and clearly mention if these parts are stationary or rotating. So, in the left side, we can see that uh, the inside is rotor and the outside is stator. And we can say that DC machine is made by mainly two components, rotor and stator. And the rotor consists of the windings and the electromagnetic core and this commutator. And the stator part is this part, the winding part, and the electromagnetic frame, as we can see from the third graph. And we can also say that the brushes and the circuit is in the stator part. So in those armature components are rotating and the stationary parts staying in the same. So I hope I didn't forget anything, and let me move to the next question. The second question is, define and explain the electromagnetic forces acting in this machine. You can show the direction of the tangential force at assumed field and armature excitations at an assumed rotor position. We have two types of force in this case. So one of them is Lorentz force and the other one is reluctance force. So this is not salient, but in the salient case, we have reluctance force. Let me explain the reluctance force. The reluctance force is, in the nature, the magnetic field lines wants to shorten their length. So in order to shorten this length, this part starts to move in the clockwise direction. So when we come to the Lorentz force case, it is the used in this case, the first case. It is F equal to IL cross product B. So we can assuming that the magnetic field is a downward direction. So in this case, by the right-hand rule, we can clearly see that the force is to the left side. And when we look for the components of this force, this is the normal force and this is the tangential force that results in the rotation. The same thing is valid for the other side, because in this part the current is direction of the current is changed, and by the right hand rule, this is the force, this is the tangential component of the force, and this is the normal component of the force. So I think that is enough for the second question, and let me move to the third question. The third question is, explain the role of commutator and brushes in a DC machine and clearly mention if those parts are stationary or rotating. So in order to maintain the rotation of the motor, we need to do something. One of the solutions can be the changing of the magnetic field, but in this case, this is the permanent magnet, and the other solution is the changing the current, the direction of the current. So in this DC case, we need to do something else because we cannot change the voltage like AC. So in this commutator, we can see that we have a gap in here, and this part, this brush is connected to minus and this is connected to plus. So the current is flowing in this direction. But when we turn the motor at this point, the gap will be on this part and this gap will be on this part. So after that point, the X component starts to touch to the plus terminal of the voltage source, and Y component of the commutator starts to touch the negative terminal of the voltage source. So as can be seen clearly, the brush is stationary and the commutator is rotating. So let me move to the fourth question. Fourth question is, show the equivalent circuit of a DC machine, armature and field. Explain the induced voltage and torque equation. Since we have a rotating, I want to explain the second part first. Since we have a rotating loop in the magnetic field, an induced voltage will occur, and this can be written like, sorry for my writing, this is flux, and the flux is basically to be RL. So when we look for the induced voltage, it is equal to 2n Vmax, sorry, Vmax 2 pi, sorry, 2n phi, and this can be written like k phi Vm. This is basically the induced voltage, and this part is the machine constant. So when we look for the torque calculations, the power EM, which is here, is equal to VA IA minus IA squared RA is equal to EI. And we can see that in this part is the VA multiplied with IA, and this is the power dissipated in the resistance, and this is the power that is left. So also we know that the power is equal to torque EM Vmax, which is found as EA IA. So in conclusion, TEM is equal to KA and IA. And this is the same machine constant. So from this we can see that we can control the torque by controlling the current. And I took these graphs from the lecture notes, and this is the basic DC circuit of the circuit of the DC machine. This part is the terminal part, and this part is the rotor part, and this part is the winding part that makes the magnetic fields. So let me move to the last question. Last question is, explain the power flow in the motoring and generator modes with the help of an equivalent circuit. So as it can be seen from the graph, if VA bigger than EA, the currents flow into the motor, so it is the motoring action, and the otherwise it is the generator action, because probably somebody turned the motor and the induced voltage will be increased because it depends on the Vmax. So if the current will be flowing through the terminals of this, and the other words, P Mac is equal to PEM minus PMAC losses. So if PEM is bigger than PMAC, it will be motoring, and in the other case, probably somebody turned the motor with wind or with their hands. PEM, PMAC, this will be generator. This will be motor. And as the last part, I want to draw the power flow. So in the motoring case, the input is electrical, P-in is electric. So we have electrical losses. We can say that it is R square R. And we have some magnetization losses due to the eddy currents and hysteresis magnetization power loss. And this is the PEM. And we reach the rotor part, and after that we have the mechanical losses due to the windage and the friction between brushes and brushes and the rotating parts with the air. And the P output is the mechanical power. In the generating case, the P-in is mechanical, and we have the windage and friction losses in the rotor side, the rotation side. P loss mechanical. This is the PEMs, and after that we have magnetic losses, and after that finally we have the electrical losses, electrical power losses, and we have the P output as the electrical. So in this case we can see that those are turnable. So I think that's all for this video. Thanks for your attention.